Следующий спикер конференции Дмитрий Ветров, автор.
Our next speaker, Dmitry Vetrov, the author of Bayesian regularization and graph models research. He is the head of deep learning at Higher School of Economics and the researcher at AIRI. He is going to present the secrets of how you... Thank you, colleagues. Thank you for the invitation. I'm so sorry I can't be there in person, but I hope that even though I'm presenting remotely, it still will be good, it still will be interesting, given the experience that we've gained in the last several months. So my presentation will be about the unusual property that occur in over-parameterized models of machine learning, meaning all the modern neural networks that contain way more parameters than there are objects in the training data set, in the training sampling. So this over-parameterization, it leads to very interesting effects, which I would like to touch upon today. We will start with the gap, the seeming gap between theory and practice. We'll move on to the interesting properties of such over-parameterized models, and then the problem that I got especially interested in lately, the double descent. What causes it? What is it? It's very interesting to review the causes for it. And if we have time at the end, we will talk about the aspects of optimization in over-parameterized models, because there are some interesting effects there as well. And some of them have been discovered this year. So this gap between theory and practice, where does it come from? We all know from machine learning courses at university, the classical statistical theory, statistical learning theory connects the risk and the flexibility of the model. There you have the classical U curve, and if the model is too complex, if the model is too flexible, there is a gap between the training error, the empirical risk, and the test error. The more complex the model, the bigger the gap, and the model starts getting overfitted. There have been different attempts at trying to determine what the difficulty is about. Maybe it's the Lipschitz constant or sensitivity to input data. Basically, it's the same thing, just from different angles. Qualitatively speaking, everyone understands what a complex model is. It is primarily about the number of parameters. So we know that the modern practice of deep learning shows that the bigger the flexibility of the model, the more parameters it has, the higher its training capacity. But the theory and practice exist in a situation of a gap between them. But, however, this is not quite the case. The theory talks about the worst-case scenario. We know where it comes from. We're not just tying the empirical risk and the average risk, the training error and the general aggregate error, but we're also introducing the minimization of the training error. And to correctly assess the this error, we have to take the worst-case scenario, because that was the case for classical models. So there is no contradiction between theory and practice, because when we train neural networks, we're not talking about the worst-case scenario. And secondly, if we purposefully try to take a modern over-parameterized network and find the weight values that give us zero training error and whatever error with the testing dataset, we will see that very easily we can find a lot of such weight values. This is one of the recent publications where the authors showed that the modern methods of neural network training are basically crossing the minefield. So this is the starting point, and with stochastic optimization we get to the finishing line, the finishing point, and all along this trajectory there are weight values that give you zero training error and whatever testing error. In terms of optimization functionality, they are perfectly suitable. The training error is zero, and this is a great illustration to the fact that there is no gap between theory and practice. These minimums are exactly what theory predicts. It says that if your model is over-parameterized, you will have these amazing minimums with the bare generalization capacity of varying values, and that's the case. That's what we observe. Why are we not finding them with our standard training methods? Let's first talk about the over-parameterization of models. What does that mean? This means that in a model, the number of configured parameters is way above the training dataset, and what that means is that we practically always can achieve zero training error, as opposed to under-parameterized models where we do not achieve the zero training error. Specifically, we can achieve this zero training error even if there is a lot of noise in our data, or even if there is no real correlation between input and the correct answer. Even in this case, we still can just remember the training dataset and achieve the zero training error. So these are the surface external parameters, properties of such models. One of the key and interesting features of them is the mode connectivity, discovered not that long ago. As opposed to what has been the consensus for a long time, there is exponentially a lot of minimums, but isolated. Now it turns out that they're not isolated at all. They form a linear manifold of unknown dimensionality, and any two global minimums can be connected with very simple curves. For example, like this knee-like curve. It turns out that out of two global minima, we could, in any experiment, build this path, this trajectory that connects the two, and this gives us zero training error and close to zero loss function. Of course, the manifold is way bigger in dimensionality, and apparently all global minima are connected with each other and make up this interconnected unit. What is the result of that? If we use our dear method of optimization to achieve zero training error, if we continue our training process instead of stopping, then it might so happen that we will drift towards the manifold of zero loss function with training. For example, we can drift from narrower minima to wider ones. And as we see towards the end of the presentation, we do observe just that, just this effect. Another interesting feature is the double descent that I mentioned at the beginning. This is taken from Mikhail Belkin's article, professor at California University, and I borrowed content for my presentation, some content from his articles. I really like that. If we review different models of network training, let's say we have a neural network and we will be increasing it, augmenting it. We have a small network, we'll make it deeper and deeper. While the neural network is not at the state where there is a zero training risk. The training risk and test risk, they behave in accordance with the classical statistical learning theory. So we see the reduction in training risk, and the test risk is reducing and then starts to grow.
So the model starts to retrain itself, but at the point, more or less, at the point when the model becomes so good that we can, without errors, to recognize the sample, we have the peak. And if we increase the complexity, the error rate does not change. The complexity of the model increases, so there's a zero error, but for the model it changes and it peaks. This is a very weird property that has been discovered recently. This is the summary of under-parameterized and over-parameterization. Non-zero train error for under ones. In over-parameterization, we have interpolation mode. Usually, we don't need a lot of resources to get a zero error for the training. In under case, we have isolated minima. For over, we have a manifold of zero train loss. On the left, we have so-called local convex, the isolated minimum. We can look at it as a local convex. In the situation when we have a manifold of the global minima, we cannot even think about local convex. It is easily proved mathematically that there is non-convex, and this is a principle. This is why we look at Gaussian things. We see some small negative values. So this is related to the fact that we do not have a convex. It's an interesting feature. That means that mostly all theoretical guarantees that you got for different training models are not applicable, actually. If you look about this over parameterized networks, because you need to have a local, at least a local convex, and here there's non-convex scenario. And the last one, there's an optimal complexity in the under parameterization, and for the over one, the more complex the model is, the more parameters it contains, the better. Now let's try to understand, where do we have this double descent? Can it be explained? Actually, it can be explained, and it is related to the change in the norms of the weights in different parameters of parameterization. In the classical machine learning, there are results for linear models and core methods, where we link the norm of the weights with the functional norm, and the functional norm always shows the level of constant. If the functional norm is high, we have a more oscillating behavior. This is where I actually try to show you in the diagram. These are the theoretical results. They work for linear models and core models. Networks are not neither these nor that. But there was some research that kind of showed that with some parameters, these networks start to behave like core methods, you know, like linear models, in a way. But it's understandable that it's not a surprise really, because it can be explained. At the same time, it shows a kind of a link that exists between these models and the neural networks. So you can think that in neural networks this cannot happen. If the weight norm after the training of the neural network is quite high, it is likely that this neural network has an oscillating behavior that will be very unstable, and actually the capacity will be quite bad. Now let's look at the key slide. I actually tried to do it on my tablet PC. So where do we have this double mode? Let's say we have a over-parameterized model, and the weight is represented in the arrow. The blue arrow is a multi-fold space of the weights. Since the model is over-parameterized, there is a space, there is a manifold based on which you have the training error. Usually we have some additional regularization, and that means that you should select the weights with the lower levels of error rate, so with the zero train errors. And this is where you go to the blue dot. And let's increase complexity, let's add additional weights, make it even more over-parameterized. The weight space increased. In the new weight space, you have an area where you have the error, training error, targeted train error, and when the weights are zero, you go back to this zero train error. In a more complex model, we will have a point with lower norm compared to the previous one, to this blue dot. So if we start to make these models more complicated, more complex, the weight norm is going down. So from a blue dot we went to the red dot. The weight norm decreased, which means that the oscillating behavior decreased and the generalization capacity increased. Double descent, let's look at that again, and let's see what will happen if we increase gradually the complexity of the model. Under parameterized case, our model cannot be trained. We have the regression. We tried it, as you can see, but the error is there. We're increasing the complexity of the model, so now we achieve the complexity. We have an ideal sampling, but the weight norm is quite high, and experiments showed and confirmed that. We continue to increase the complexity of our over-parameterized model. The weight norm increased, but the sum norm goes down, and it is confirmed by experiments in our papers. We have a more less oscillating behavior with a better generalization capacity, and that means that the validation error goes down. This is a counterintuitive attribute on the one hand. On the other hand, we were able to, get it. If in over-parameterized models, if in under-parameterized models you increase the complexity, that might lead to the conclusions I just talked about. Obviously, to make sure it all works, we need to regulate it additionally. The continuum of solutions with zero train error, among these we have to select something good. What are the parameterization methods? These are the types of regularization. Weight decay, implicit regularization, that is caused by stochastic gradient descent. The gradient descent can be used for the global minimum, and the gradient descent also supports the convergence to the wider global minimums, which is good because there is a hypothesis that is confirmed by this community that the wider minima has a better capacity than the narrower one. Now, there was an article, Lobachova, 2021. The batch norm uses a stochastic ingredient and regularization. In combination, it gives a great effect that can encourage the convergence to the wider minima. Now, this is an exciting experiment in terms of the influence on the step, on the distance of the step. The bigger the step, the bigger the dispersion between the stochastic steps as part of the stochastic gradient descent. High dispersion of the steps. What does that mean? That means that in some way, our optimization method has a less decisive deciding power. The landscape will be very complicated. There will be different canyons and other things, and we do not really know what are the barriers. Even if we are in our even if we don't see it in the first instance, we will understand that there's a problem in the second one. So, intuitively speaking, we think that the higher the step, the higher the dispersion, the better. The higher the convergence. But you can select the width of the step when the neural will just be destroyed. There will be no convergence at all. There will be absolutely no minimum, wide minimum. So let's make an experiment. Let's have an approximation and convergence, and let's have different steps. And we'll use stochastic gradient descent. Very low values for the training function and the zero error for the classification, but we were able to converge in all errors, but in terms of the error we have a totally different global minimum, although we started with the same element. And the wider the step is, blue one is the lowest one, orange a bit more, and green one 2 steps more. The wider the step, the lower error rate on the test. So the better the training capacity. If you look at the minimum point, and you can see that with the cross, the point in the weights where you achieved the needed value, and we can build a Fisher matrix that is a good convergence that describes the curvature of our global minima. And here we can see, and which was predictable, that the smaller the step, the more values, the higher the curvature, the lower the minima. The lower the step, it minimizes and it improves the training capacity. All that testifies to the fact that we are right now not using the optimal ways to train neural networks. So we do not have any theoretical guarantees because there is no convex, local convex. At the same time, we see that the global minima, there's a lot of them. Some of them are good, some of them are bad. We need to encourage the width of the global minima, or maybe do something else. And the stochastic web averaging and sharpness-aware minimization, both quite recent techniques. They are the schemes that try to indirectly encourage the width of the global minima. And it improves the training capacity. It has been confirmed by different research groups. Yes, that helps. And with some magic, the training capacity improves. So there is better error rate. The last effect I wanted to shed light on, called grokking. I think actually someone actually put the machine for training, nothing worked out, and they actually left the PC switched on, and the model was being trained for a weekend, I guess, or something like that. But anyway, there is a test sampling, a neural network, a training sampling. We launch neural network, and let's see the accuracy. The neural network achieved something, and the accuracy 100%. At the same time, the validation accuracy is quite low, and you can see the scale, algorithmic scale, several factors here, and then the test and the validation error accuracy goes to 100% as well. And this is tens of thousands of iterations we're talking about on the X. Why does that happen? The training process should have been stopped, but the neural network is continuing to do something. Something happens, and then this something, you know, the quantity goes to quality, and at some point we start to generalize unexpectedly. So we have the training sampling, and then we put it to the testing sampling. It is related to the fact that maybe that we have a manifold, and we can put it we can go from the narrow minima to the wider ones. And that improves the training capacity. And this is the conclusion. Over-parameterized models significantly differ from the classical ML algorithms and models. In richer families, the global minima with better properties exist. So it makes sense to use over-parameterized model as over-parameterized as possible with your memory. Implicit regularization is of extreme importance, and we need theory scientists who would actually create the regularization and explain regularizations. That would maybe have a better training of the models. Thank you very much. Thank you, Dmitry. Several questions. What are the main barriers right now for the deep learning? Well, I would say that the main barrier are the technical ones, related to the fact that not many research groups have access to the advanced resources that can train very wide neural networks. The less access there is, the less progress we have. The leap-throughs in the machine learning we had in the last decade and 15 years was related to the fact that the scientific community got access to the very cheap and powerful equipment. If we take the healthcare technologies, how can they help the situation related to COVID and pandemic, for instance, in Russia? Is it possible? Well, they are doing it as we speak. What are the other ones? What can be the other ones? There are some research papers that talks about the AI models for diagnostics and for building new connections with the different attributes. And also the models are used for forecasting of the outbreak, possible outbreak in the future. Okay, let's take the young data scientists. What do they need to focus on right now? Well, I would be subjective, maybe I'm biased here. So I would say that the most promising area are technologies related to NLP. These are text models, because maybe thanks to them, models like GPT-3 and CLIP, maybe thanks to them, in the nearest 1.5 years, 2 years, we'll be able to make a large step in the development of AI, and we'll be able to get the system that will be able to resolve many tasks. And just the last question from me. How can you How can you so quickly say over-parameterized models? Well, Ekaterina Schulman is my teacher here. Well, thank you very much anyway. I was very excited.